Okay, hi everybody, and welcome to our final foundations talk for the semester. It's my pleasure to introduce Jaco and Swart, who will be talking, who's from MIT, and we'll be talking about how dark matter came to be.
Thank you so much. Thank you so much for having me here and finally being able to say something. I guess most of you have seen my face around sometimes. And I am at MIT. I work with Dave Kaiser on the history of physics and particularly on history of dark matter. And I'm writing a book about that. I wrote my thesis about that. And done some other projects recently, more on the anthropology of dark matter. But here I'll say something more about this project, my history project. And I'll give a broad overview of some things, and then we can delve into some questions if you would like that. But I always start with a question, especially on a Monday morning. I would like to wake people up, and that's matter. This one. Here we go. Can we check if you have our keys? Do you know where your keys are? They're just I have no clue. I think they're in my jacket. I like this question of the keys because it makes me realize, when do you lose your keys? That's a kind of a weird philosophical question, and that I like very much because
You will have a daily conversation with me. I know. My students bought me an AirTag.
When do you lose something? When do you realize you lose something? Is that when you actually just randomly search for it, or maybe when you need it because you're late for an appointment or of some kind? Kelsey?
Hi.
And so when do you lose something? Okay, now imagine that you've not lost your keys, but you've lost something else. Imagine you've lost 85% of the universe. How do you realize that that's the case? How do you lose 85% of the universe? And this might be a bit of an overly blunt question, but this is for me what's at stake in my research. And we all know that this is the case, that current theories of the cosmos say that 85% of the universe consists of something that we've never seen before and is made of dark matter. And there's a huge infrastructure that tries to find this 85% of the universe. Big detectors underground. Here's a picture of the xenon detector in Gran Sasso in Italy. But I presume that most of you know that there are tens and tens of experiments, dozens of experiments, that's what you say in the US, that are searching to find what people think is particle dark. So my question is, prior to that, my question is, how did we get here in the first place? What are the conditions under which people started to get interested in the dark matter problem and start to be convinced that indeed the majority of the mass in the universe consists of something they'd never seen before? In other words, my question is, how did dark matter come to matter? So I'm interested in these historical conditions to try to understand what was happening in and around the 1970s that indeed physicists and astronomers started to introduce this idea that the majority of the mass of the universe is unseen and invisible. And that's what I wrote what we'll talk about is a part of the book that I'm writing, which has been featured already in another book, which is my dissertation. I brought a copy of that if you are interested in taking a look at that. And I'll survey a part of that. And that goes up until 1974. So if you see this question, some people will ask me, Jaco, we know how dark matter came to matter. That is through evidence. We know there's evidence for dark matter, and at the point that we found evidence for dark matter, and two names that are often associated with that are that of Vera Rubin and Fritz Zwicky, we knew that dark matter should exist. But then here, I guess my philosophical historical brain starts to flash, and I ask the question, how does something become evidence in the first place? Why do we consider a certain phenomena evidence for something else? Is that something that is obvious? Is when we see something or observe something, is it obvious that it is evidence for something, or is there something more at stake? And of course, my thing here is that evidence is not something that is given. It has to turn into something. Observations have to turn into evidence, and that's a certain process. And that's something that we'll see here in the history of dark. So this is kind of the upshot of what I would like to show, and that there are two phenomena that became evidence for dark matter, but only after major changes in what it meant to do cosmology in the 60s and 70s. So I'll also give a survey of that. I'll show you the following. I'll discuss the history of two issues of mass, and these are issues that we currently consider to be evidence for dark matter, but I'll show that this wasn't as obvious as we think it was. And then I'll show how mass went missing, and I'll give an overview of the changes in cosmology that I just mentioned. So I'll start with the first issue of mass in galaxies, and that has to do with clusters of galaxies. And with the name that's often associated with that is Zwicky. And this is what a cluster of galaxies looked like in the 1930s. Not as fancy as the pictures that we know today. This is the Kumar cluster of nebulae. And in the 1930s, we have to think that it was just after Hubble and others had introduced the idea and became convinced of the fact that our own Milky Way is not the only galaxy in the universe, which happened in the late 1920s. So understanding the distribution of galaxies in space was a new question that people were asking in the early 1930s. So this is one of the early ideas about, or the early products of that investigation, thinking about the distribution of galaxies in space and about the fact that they would be clustering together. And one of the people who investigated this, indeed, was Fritz Zwicky. And Fritz Zwicky came to Caltech in the 1930s on a Rockefeller Fellowship. He was going to work with Robert Millikan, but instead he decided that he wanted to do cosmology and astronomy. So he became a colleague of Edwin Hubble. And Fritz Zwicky was quite critical of Hubble's idea of what we now understand as the expansion of the universe, or the velocity-distance relation as it was introduced at that time. And especially, he didn't really believe that redshift, we should understand redshift naively as velocity. So he went to look into a lot of the data of Hubble, and he wrote a little piece because of that in the Swiss Physical Society journal. And he was very critical in thinking about maybe this redshift is a gravitational redshift. It's something that he called, or others had called, gravitational drag, and that there's something else going on other than what Hubble had said. And in one of these paragraphs in this quite long and eclectic paper, he studies this Kumar cluster of galaxies. And what he noticed is that the velocity of dispersion of these galaxies is very, very high. So the random velocity of these galaxies moving throughout the Kumar cluster is very high. And then he gives us some observations about it. He said maybe that is a sign that we should understand redshift differently, so that velocity is not just inferred simply through redshift. Or he says if we do accept that, then maybe there should be some extra mass that stabilizes the system, because if that's not there, the system must be dissolving. And that's a note that he made in the 1930s. It was a note that was quite influential around that time, and specifically in where he was. There were a few others who started to work on that. But and that is, so some people would say that it wasn't taken seriously because Zwicky has been notoriously been a kind of a weirdo. There are a lot of stories that I've heard. I've done a lot of oral history interviews for my research. There are a lot of stories of Zwicky, which I'm gladly tell you after this. But I think there's a much more mundane explanation for why people didn't pick this up, because it was quite well known, this issue in the 1930s at Caltech. But what was the case is that actually the idea of that clusters are fundamental condensations of matter in space, that wasn't accepted yet in the 1930s. And actually, there wasn't data yet on this. So it was only after the war that with new sky surveys, as they call it, that people started to get an idea of that.
So was Coma the only known?
Virgo and Coma, and there were a few others. I think there was a handful, maybe a dozen. Which and this increased almost tenfold to the 1940s and 1950s, and this is one of the instruments that they did this with. This is the one that they did the Palomar Observatory Sky Survey, which was one of a very, very influential sky survey that mapped a part of the sky and the distribution of galaxies in there. this is something that really fed into the growth of extragalactic astronomy. And the whole notion of extragalactic astronomy was something that people started to discuss much more in the 1950s, late 1950s. And then you have people reflect on this idea of clusters of galaxies. That was a big discussion that people were having. On how many levels do we see clustering at? And well, one of the things that they started to notice is that indeed clustering is fundamental. So here you have a quote from Zwicky in 1956. Contrary to opinions previously held by astronomers, clusters and clouds of galaxies are the rule rather than the exception. So this became a hot topic, one of the topics in extragalactic astronomy in the late 50s. And with it, they saw this problem that Zwicky had seen. This problem with the dynamics of clusters of galaxies. There's something going wrong in the movements of these galaxies. And it seems that there is that this Zwicky problem, as people call it, held for a lot of these clusters that they found. And what was actually happening at that time is that there was a whole conference session or pre-conference devoted to this idea. This idea, what people called the instability of clusters of galaxies. And this happened in 1961. So who recognizes this place?
Berkeley, right?
It's Berkeley, yeah. So this is the IAU general meeting in Berkeley in 1961, where they all hang outside. Who has ever had a conference outside? How nice would that be? I would really enjoy that. This was actually the largest IAU to date in 1961. They had just opened general membership to the IAU, so it really exploded at that time. And one of the sessions that was held there was a session on the instability of galaxies. And the incoming IAU president, the outgoing was Jan Oort, a famous Dutch astronomer, and the incoming was Victor Ambartsumian, was a very famous Armenian astronomer. And he had introduced a very influential idea trying to explain this Zwicky problem. So there were two ideas that people discussed in the symposium that in what could happen in these clusters of galaxies. That's either as there's an excess of mass, there's some invisible mass which makes that these clusters are held together and that this velocity.
But Dickey already proposed Uncle Materi in his own paper.
He proposed, yeah, for the coma cluster.
Right.
So what people are now discussing were dozens of galaxies in which they saw different things happening.
Going beyond coma.
Yeah,
more
beyond,
generically.
more general, many more, and even smaller systems, the groups of 5 to 10 galaxies where they saw that this was happening. And one of the things that they discussed at this pre-symposium was that there might be a sign that there is excess of mass. But the idea that was discussed much more, it was controversial, but a lot of people were very interested in this, and that was Ambartsumian's idea, is that there was an excess of energy. So that what they were seeing, that this high velocity dispersion of galaxies was actually showing that clusters of galaxies are not stable at all. So every cluster is an expanding cluster. And that's, of course, now very interesting, but at that time, they didn't have a sense of the formation or a theory of the formation of galaxies and clusters of galaxies. So his idea was that there was a seed, somehow a seed galaxy that made, and some matter was formed, and there was some way that clusters of galaxies were formed from a seed and were expanding, exploding apart, as he would sometimes say it. And this was very controversial, but very influential. And so what you see at the end of the session is that people didn't really know what the solution to this problem would be. Both had issues with them. And one of the things which was very interesting at the time is that there was a lot of visual evidence, that's what Ambartsumian said, that there was some explosive phenomena going on in galaxies and clusters, and that is something that we now consider to be active galactic nuclei. So the first images of these things were coming out in the early 1960s, and Victor Ambartsumian interpreted that as having an explosive energy in. So at the end,
This energy is not a reference to dark energy or anything.
no,
It's just-
no. It's the kinetic
Excess
energy.
kinetic
It's
energy.
the kinetic energy of the system.
Can you say a little bit more about what regulation is you can use? Because suppose you have excess energy, you can solve it with excess mass that will keep it together as a cluster.
So
So like if you have excess energy and the cluster can't remain stable, you can solve it with excess.
well, you can see it as you create more gravitational potential because adding extra mass, and then you make the system stable, or you say that actually the amount of kinetic energy is inherent to the system and makes that the system will dissolve at one point.
Okay, so like the first one is to keep it constrained. And
Yeah. So there were, so what I haven't discussed here is that the theorem that was at stake in these things, what people call the virial theorem, which was a relation between the potential and the kinetic energy for a system, and that's the way that they mostly discuss these issues. And two ways to address the way is that either you're going to make them stable by adhering to this virial theorem, and then you need to add extra mass, or you accept that the virial theorem doesn't hold for the system, and that's something what Umberto did. So this is one of the conclusions at one of these sessions. For any particular group or cluster, it seems at the moment to be very much a matter of taste as to which explanation of the apparent dynamical state of the cluster is assumed to be correct. And this discussions on this continued in the 1960s, and particularly because high-end astrophysics became became a discipline because of the space race in the birth of X-ray astronomy, the birth of gamma-ray astronomy, all happened in the 1960s, and because of that, people got a better sense of what mass would exist in if there's ionized stuff in clusters of galaxies. These are very interesting discussions, but I would kind of like to shift to 10 years later, people talking still about the same problem. So in 1971, there's a review of what was going on still in this about this issue, and that in that review, the people say that neither hypothesis, hidden mass or quick disintegration, can be eliminated at present. So X-ray and gamma-ray astronomers had not found any signs of mass that would be able to bind these clusters. And at the same time, the quick disintegration hypothesis meant that we need to find galaxy clusters that have been dissolved. Where are these dissolved galaxy clusters? We don't see them. And that was an argument that many people doubted this quick disintegration hypothesis. So it wasn't very clear what was happening in the 1970s. And what's very interesting is that what happens is you see a lot of astronomers and physicists take up this idea to see if they could or integrate it in their work, which was in a different subfield. And here's a series of different explanations. So some people worked on dwarf galaxies and said maybe it's dwarf galaxies that can solve these issues. Others had introduced neutrinos as a potential idea of solving this problem. There were even suggestions of the existence of a different force law, and then you work with a negative lambda, so to make sure that you can stabilize these clusters instead of having them explode apart. Maybe we're mistaking member galaxies of clusters for field galaxies. Maybe it was instability at all, and some people even thought that if we just look good at the data, that wasn't the problem at the time. And one of the most interesting one I find, at least, was a suggestion by Stephen Hawking, which he did in this very famous paper that I think most people here at the institute know, where he introduced the primordial black holes. And one of his suggestions in this paper is that if you introduce primordial black holes and a distribution of black holes, is that you can solve this problem in clusters of galaxies. So he thought of it, if we want to do a bad reconstruction of history, as the first idea that black holes could be done there. This is what he says in the paper. It is tempting to suppose that the major part of the mass of the universe is in the form of collapsed objects. This extra density could stabilize clusters of galaxies, which otherwise appear mostly not to be gravitationally bound. So that was another suggestion that people had. And my point here being is that how to solve this cluster discrepancy was very much a matter of taste. We now think of it often as evidence for dark matter, but this wasn't the case in the early 1970s. It wasn't very clear what this meant and how this, how every part of this problem could be explained in a certain way. So that's the first part. In tandem, independently, another issue rose in astronomy in a different subfield of astronomy, and that's galactic astronomy. And this story also starts in the 1930s, and this is the Andromeda system, a very cute black and white picture of made in the 1930s. And we go back to Hubble again, because after what Hubble had introduced, or that people started to be convinced that galaxies exist external to our Milky Way, it became interesting to study the properties of these galaxies. And something that Hubble didn't do. Hubble did mostly cosmology, but other people started to get interested in understanding the properties of these galaxies and especially also their rotation. How does gas move in these galaxies, and what gas exists in galaxies? And one person who studied that was Horace Babcock. Horace Babcock was a student at Berkeley, and he used some data to check the existence of gaseous nebula in the Andromeda system, and to look at the velocity of these nebula. And that's what you see happening here. So the above picture is a picture of the Andromeda, and the circles are the gaseous nebula that he had identified and looked at to see what the velocity of these nebula were. And he made what we now understand as one of the first rotation curves. Well, it's not actually a curve. This is, I don't think you can call this a rotation curve. There's a set of data that he plotted the velocity as relation to the distance from the center of the galaxy. And what he found is something very interesting, and that's he noted too. It seemed that the velocity seemed to increase linearly. And it was around this time that a debate started to evolve, or an idea started to evolve, is how should these galaxies rotate? And Babcock referred to this as a planetary model of rotation. That the way that people thought about this is that galaxies should turn around like planetary systems do. And that's something that we now often call a Keplerian rotation. So that the rotation decreases with 1 over the square root of r with distance. That's not something that he saw. It appeared that his data, and that's at least what his supervisor showed in this data, didn't really work. And a lot of people, also Martin Schwarzschild in a little bit later in the early 1950s, showed that this wasn't really the case. And people started to think of galaxies mostly as abiding to this planetary law of rotation. So this is one of the first introductions, but it was only, again, much later that people started to become much more interested in that. And that was the same reason as for the galaxy clusters, is that there wasn't much data available about gaseous nebula in galaxies. And that was only much later that people, that astronomers started to theorize these ideas and look into that much more. And that was with the rise of radio astronomy, which happened in the late 1950s. Here you see the 300-foot NRAO telescope, one of the early radio telescopes that was set up. And with radio astronomy, people could now look into neutral hydrogen and find new gaseous nebula in galaxies that reached much farther out than before. But it wasn't only that, the radio astronomy, it was also the technique that they used in radio astronomy, and that's something you're also quite familiar with, which is interferometry. So interferometry became a thing in the early 1960s, and this is the Owens Valley Radio Telescope where they started to apply this technique. One of the early places that they started to apply it. Another place is the Westerbork Synthesis Radio Telescope in the Netherlands, that the group of Jan Oort was working. And with all these new developments in radio astronomers started to look into the rotation of galaxies. At the same time, also, we see a very interesting development, technological development, which was the photomultiplier tube that started to be used and was developed near Washington, D.C., and started to be used by Vera Rubin and Kent Ford in several different telescopes, which also meant that they could resolve new areas optically, specifically in Andromeda, which they started to study. So what you see in the early 1970s is that a lot of rotation curves were popping up from radio astronomers and from this group, Vera Rubin and Kent Ford. And here you see several of them. You see on the left, the above left, you see the Vera Rubin Andromeda curve. On the right, you see the ones that were made by the people in Owens Valley in California, the radio astronomers. And in the left corner down, you'll see the ones that were made with the Westerbork Synthesis Radio Telescope and with the NRAO telescope. This is a big set of new things that were coming out. And now, as one of my interviewers said to me, why didn't people see this? Why didn't people scream from the rooftops that this was flat rotation curves? Because they didn't. That was not happening. As some people would say, that is what you see here. You see a lot of extended flat curves that would signify that the rotation is not abiding to the 1 over the square root of r, as people thought the planets would rotate, but that rotations are much faster in the edges of galaxies. Now people arguing that means that there should be extra mass. But that's not something that any of these authors were arguing at that time. And that had a very particular cause, and that, well, two of them actually. So the curve that they used, many of these curves that they used, some of them were called the Brand rotation curves. And in these curves, what happened is that they baked in an asymptotic behavior. If you go to very high values of r, they baked in that they would become a 1 over the square root of r formula. So that's what happened to most of these rotation curves, is that what you see here is still something very flat, but you could make these parameters so that in the end you will have a declining rotation curves. And then, so if you read these papers, most of these authors would say that although these were very flat features, they couldn't say anything about the mass of these galaxies. Rubin and Ford wrote, extrapolation is clearly a matter of taste, so meaning the extrapolation of the data beyond the last measured point. So they didn't even give a measure of the mass of the galaxy, because it didn't say much about how extensive this galaxy was. And some others in this paper also said any extrapolation of mass is very uncertain. So again, a matter of taste, as you see here. So that's my point here, is that these flat rotation curves, things that we now consider evidence for dark matter, weren't considered in that way when they were observed. It was a matter of taste on how to interpret these flat rotation curves, as was the case with this problem of Turkey. So these are quick overviews of the history of these two problems. Much more is to be said about that. But I would like to go into the second part of this talk, and that is about how then should we explain that people started to get interested or started to interpret these these observations as evidence for dark matter. And for that, we have to zoom out a bit, and we have to think about something that the next speaker will also be saying some things about, and that is how cosmology was changing as a field in the 1960s. So this is about how this mass went missing. So this is the amount of the number of people that were working in astronomy in the 1960s, which increased in a threefold, and that was because of the space race. So NASA was set up in 1958, and because of that, there was a huge increase in the workforce in astronomy around that time, and the amount of PhDs that were granted in astronomy. But what's key here is wasn't just the amount of PhDs, it was also the type of PhDs that was that astronomy was putting in. So the amount of people that had a PhD in physics and astronomy increased from 25% in 1966 to almost half of all the people in astronomy. They didn't have a degree in astronomy, they had a degree in physics. And by 1970, you see that theoretical astrophysics became the central interest of most astronomers. So there was a huge shift in what people were thinking about and who was doing this.
Sorry, is that 25% of all? What is it? What is that statistic? I don't understand.
Okay, and so of all the people that have a PhD in astronomy in 1966, 25% they were PhDs in physics. And by 1970, it was 45% of everybody who had a PhD and was working in astronomy had a PhD that was from physics.
25% of everybody who's working in astronomy.
Yeah, with a PhD.
I mean, this is just showing you're not making an argument about physics versus astronomy
No.
PhDs.
No,
Just the number of people has gone up by 20%.
yeah, I make an argument about who was doing astronomy with what background changed significantly in the 60s. So a lot of people had a physics background rather than an astronomy background in the 60s, and that was
Were
becoming.
there even astronomy programs, PhD programs?
Yeah, so a lot of most programs started to become physics and astronomy programs in the 1960s. So there was institutionally a huge shift towards physics in astronomy. So astronomy was classically something that was part of mathematical, was often made part of mathematical programs. But by the 1960s, that changed very much. And this was also related to a lot of observable things that were happening, a lot of new phenomena that were being discussed and discovered in the 1960s. And I'm not sure if somebody here in the audience knows what this picture is a picture of. Maybe on the Zooms. This is 3C273. The first quasar. That was observed in 1963. And this quasar was at a historically large redshift, which was a redshift of 0.1, which was something that they hadn't seen before. They had seen one before, I think, one object before around that. But so it was very, very far away and very, very bright. And this made that the way to explain the brightness of this object was a mystery to a lot of astronomers. And what happened because of the quasar is that the first Texas Symposium in relativistic astrophysics was set up also in 1963. And this was a summary of the meeting there. Shuking opened the scientific meeting by wittingly calling it exotic astrophysics. The first symposium in Dallas in 1963, he said, considered in great haste quasi-stellar sources. From now on, abridged as QSS. I'm glad we stuck with quasars instead. And models. The suspicion was rising that time was in to bring physicists and astronomers together, for cosmology seemed to necessarily become the field of research. And that's the point that I'm getting at, that cosmology as a field of research started to mature and being taken seriously. It's something that we can, I'll delve in a little bit. Another one of the observations that helped do this is it was done with this telescope, which was just saved from being destroyed. I'm not sure if you've heard about the radio antenna that helped discover the cosmic microwave background radiation was about to be destroyed, and it's in Holmdel in New Jersey. And I think there was a fund, people who got some money together to make sure that it now was acquired. So the cosmic microwave background was discovered in 1965. After that, pulsars were also discovered. So there were a lot of new observables and new phenomena that came out in the 1960s that really made people started to people started to get interested and work much more on cosmology. And here you see the number of publications on cosmology in the 1960s. Increasing by tenfold. This is not the relative increase, it's an absolute increase, but it's still it was an amazing increase in the amount of papers that people put out.
So how did you get these numbers? Because cosmology was word search. Was it a?
This is the ADS. This is from the ADS and the times that or cosmology mentioned in the abstract. That's
The abstract.
the way that I set this up. Yeah, so it's an indication of the interest in cosmology around this. So what you get in the early 1970s is that people start to get an increased confidence in the hot Big Bang model. This is from a review paper on cosmology in 1970. Topics which in the past were questions of pure speculations have become susceptible to detailed quantitative analyses, which can be checked against the observations. So this had to do with the cosmic microwave background. This had to do with quasars. This also had to do with Big Bang nuclear synthesis. So there were a lot of questions that people started to get interested in and took the idea of the Big Bang and cosmology much more serious. So this is what now very briefly have discussed, but what I've been calling a rebirth of cosmology, and some people would have called the birth maybe of physical cosmology. So a new way of thinking about the universe that wasn't Hubble and thinking about the redshift, the distance relation and making Hubble diagrams, but asking physical questions about the origin of galaxies, about the origin of the universe and the evolution and structure of the universe. That was influenced by the things that I just mentioned and many other things. So what was this cosmology? What was this rebirth of cosmology? Was a very new take on what cosmology was. And this is a review by Alan Sandage, Hubble's protege, who in 1970 still called cosmology a search for two numbers. Precision measurement of the rate of expansion, so the Hubble constant, and the deceleration of the universe may soon provide a major test of cosmological models. And this was a very classical idea of cosmology, how you would do cosmology. You find the Hubble parameter and the deceleration of the universe, and that's how you make the model of the universe. But this fundamentally changed. So people started to get interested in very different parameters that you could probe physically and were much more local. And instead of the deceleration of the universe, in the late 1960s, there became a new parameter that could help determine the cosmological models, and that was the mass density of the universe. That could also say something about the destiny. So this ideal that some people are still working with, that knowing the density of the universe is knowing the destiny of the universe, was something that people started to get and work on in the late 1960s and early 1970s. So what it could say, the amount of mass in the universe could tell you something about how much gravity there was, and which meant that you could say something about whether the universe would be expanding forever or whether it would collapse. So they were looking for this parameter, omega. But there was a little thing, a little preference that was still lingering in cosmology about what this mass density could be. So here's Wolfgang Rindler saying, philosophically, there might be a preferred choice of what exists, or what universe that we would exist in, and what is the correct model of the universe. And this is that omega is larger than 1. What does this mean? This means that the universe is closed, that there is so much mass in the universe that the universe at one point will stop its expansion and collapse back again. And this was an idea that was deeply rooted, and I would love to chat more with Cliff Will about this. It was deeply rooted in GR and our sense of what GR is saying about the cosmos, that the universe was closed. And you see this preference in a lot of papers, also in a lot of interviews that people had done around the time. The idea that there was something attractive of having a universe that was closed. Bob Dickey, that was Jim Peebles' advisor, would say that it would be interesting to have it closed because then you could have a cyclical idea of the universe. Some people actually were convinced that it was closed because of Mach's principle. Yeah.
Quick question in
Yeah.
the chat. If omega is 1, then the thing is, so Eric,
A finite universe.
it's flat as it's 1.
If it's 1, it's flat. Correct. Yeah. So and closed is something that would be 1 or higher. I think a flat this is something that confuses me very much, whether you can say the universe is closed when omega is equal to 1. And I'm not sure if cosmologists here can help me with that, but that's something that
Has to be greater than 1.
has to be greater than 1
It
for
has to
it
be
to
1
be,
plus epsilon.
yeah, for it to be considered a closed universe. So that is so the idea of a flat universe was something that others had preferred. So Dennis Siamat, Stephen Hawking's advisor, had said that omega is 1 for him was interesting because then you would have a balance between the kinetic energy of the expansion and the gravitational energy of the mass, which would make that it would be a natural way to have inertia related to the mass of the universe, because you then equate the kinetic energy with the gravitational energy that exists in the universe. So these were philosophical ideas informed by Mach's principle about what the universe would look like.
I have a question. Was
Yeah.
everybody at this time that was doing cosmology also just using tools from GR, or were they also doing other classical, like Newtonian theory, other classical theories? At the level of sort of
Far left, far down.
It was all Friedman equations.
Yeah, Friedman equations were out there already from the 30s.
Yeah. So it's that is
nobody ever questioned whether GR works on the largest scales and trying
so
to.
this is an interesting question, because that was a discussion in cosmology in the 1950s. So this was a discussion at the time that people were discussing the steady state cosmology, where people were people like Fred Hoyle and others, mostly British astronomers, were questioning whether, for example, the cosmological principle will hold, or whether the homogeneity of the universe would hold everywhere. So for them, that meant that they had to have a bigger cosmological principle, which would say that the universe was unchanging in time. So there were discussions about whether the laws of physics would hold everywhere, and one of the ways to solve this for them was to say the universe is in a steady state, which means that the universe always looked the same everywhere, which means that you can assume that the laws of physics were everywhere the same. So these were discussions that were happening, but not too much anymore in the 1970s. This was a little bit before that. And that's so interesting, and it's another thing that I've written about, is that this shift away from more philosophical talk like this that happened in the 1970s to more physical cosmology. And so asking physical questions and being less interested in, for example, Mach's principle, which was a huge topic in the 50s in GR and in cosmology, but most people didn't stop talking about it in the 1970s. Okay, but if you wanted to have a closed or flat universe, then you had a little problem, because what the data was saying around the time, given from mass distributions of, or given from distributions of galaxies, is that omega was only 0.01. So it was only a 1% of a flat universe. And that's something that people measured with the use of galaxy models that came out in the 1970s and the distribution of galaxies, so they could get a sense of the mass density in the universe.
So this is calculated only from the visible matter.
Yeah. So then you have a new generation of astronomers getting interested in these physical questions of the universe, and one of them was Beatrice Tinsley, who, together with some other people, wrote a very influential paper, which had the following question: where can the missing mass be hiding if it is demanded on theological or other grounds that omega is equal or larger than 1? So there was this sense, this classical idea that the universe should be closed or flat. But if that's the case, these very young physicists and astronomers were writing in this paper, if you, on theological grounds, believe that this is the case, then where is all this mass? Where can this missing mass be if you want to have a closed universe? Because, like I showed, it was far from being closed. And that is actually the main way that people were talking about missing mass in the late 1960s and early 70s, that the missing mass is the mass that you need to close the universe. So it was a big topic of discussion. First of all, people were very interested in determining the mass density of the universe. And secondly, they always related to this idea of the universe will be closed or not. So this was a big topic of discussion. And I think this is the context that we have to understand, that people start to get interested in measures, dynamical measures of mass. Dynamical measures of mass that you could do with the rotation of galaxies and with how galaxies move in clusters. So there's an interest in mass and in this missing mass in the early 1970s that came up. So then, to finish off, what I would say is the birth or the moment that dark matter came to matter is in 1974, when people, within this context of cosmology, two groups of astronomers and physicists start to interpret the rotation of galaxies and the cluster problem, the dynamics of clusters and of galaxy clusters, as a measure of mass to show how dense the universe is. And this was a group in Princeton and a group in Tartu in Estonia. Thank you. And this is a picture that I found of two people that were in both groups. On the left, you see Jim Peebles. This was a conference in the 1970s. And all the way around, you see Jan and Asta. So the group in Princeton consisted of Jim Peebles, Jerry Stryker, and a postdoc of them, Amos Jaco. And Jim Peebles and Jerry Stryker had worked on numerical simulations of galaxies before. Jerry Stryker had done his PhD with Chandrasekhar, and he knew a lot about the stability of rotating stars. And he got interested in the stability of rotating galaxies. And for that, he worked together with Jim Peebles, who knew a lot about the modeling of these galaxies in the early 70s. Amos Jaco knew a lot about clusters of galaxies, and who was a postdoc with John Bacall in Princeton in the IAS at the time, and they started to work together on this. So you have a very interdisciplinary group of physicists there. So you have Jim Peebles, a physicist, Jerry Stryker, who was, cosmologist, Jerry Stryker, who was an astronomer, and Amos Jaco was actually a trained particle physicist who just turned to cosmology. And in Tartu, you have Jan and Asta. Jan and Asta, who was a frequent visitor of the group in the...
Which one is?
Is on the right, is all the way on the right.
Right beside Asta.
Beside Asta, yeah. So he was one of the head astronomers in Tartu, in a very small village near Tartu. He would frequent Zeldovich a lot in Moscow. And
Yes.
so it's Malcolm Longhair in the middle.
Okay.
All right, that's Malcolm Longhair in the middle and George Abel. Yeah.
I saw Jerry for the first time in '82, I think.
So
He had no hair.
so this is Jerry Stryker.
Jerry,
Yeah,
Yeah.
but when?
This is in the 70s.
70s. I'm
this
saying
is-
82, it was all gone.
Oh,
It never came back.
Missing hair.
I'm missing hair from. It's amazing. The
Um,
previous one, I'm seeing so much resemblance now to his daughter, yeah.
Yeah.
Right, Eve?
so yeah, Jim Peebles and Jan and Asta. And Jan and Asta was also very interesting because he was very much a galactic dynamicist, but he started to work with the cosmologists of their group around that time, which is also a very interesting story. And Tsar, who knew a lot about cosmological models and helped him think about that galaxies could have a new population of stars. And that's how they got interested in thinking about how galaxies and the measure of galaxies influenced our understanding of the mass that exists in the universe. And here's Jerry Stryker with Zeldovich. So it was a very interesting parallel development of these things that happened in a US setting of cosmology and in a Soviet setting of cosmology. What did they do? And here's from both of their abstract and introduction of the paper. This is the paper in 1974 of the Tartu group. Evidence is presented that galaxies are surrounded by massive coronas exceeding the masses of known stars by 1 order of magnitude. 2 months later, this paper appeared in from the group in Princeton. There are reasons increasing in number and quality to believe that the masses of ordinary galaxies may have been underestimated by a factor of 10 or more. So what these people did is nothing new. What they did is they wanted to get a sense of how extensive galaxies were and how we can assess the dynamical masses of galaxies. And for that, they put together all these different measures that were done on different scales. So one was the rotation of galaxies. They had binary systems. They have groups of galaxies and clusters of galaxies. They measured or calculated the mass of these systems, and then showed this diagram. They showed that mass seemed to increase with radius in these systems. And on the left, you see very well that they combined a bunch of different scales and measurements that already existed. One was from the rotation of galaxies. You had tidal systems, which was Andromeda and our galaxies, a tidal system, how you can determine the mass of the total system through that. Binary systems, the virial theorem, the triangles that you see are the ones of clusters of galaxies. So they put all these different measures from these dozens of different already existing publications in one diagram, showing that mass increases with the radius. So the further out you measure, the more massive the system becomes. And this for them was indeed an indication that there should exist mass that we are not seeing. And the mass of galaxies has been underestimated.
So here it looks like so what is timing in this here?
The timing argument, oh, sorry, then my title of the timing argument is I think the one that is between the Andromeda and the galaxy. So the idea of the timing argument is that if they were expanding away from each other, now Andromeda is coming towards us, how then you can create a dynamical estimates of how long that would have taken. And then from that you can determine the total mass of the system. If you know how far Andromeda is away from us and how fast it's moving towards us. This is an argument that was introduced in the late 1950s. I think that's what this timing argument means. And the title must be with dwarf galaxies or smaller galaxies. I think that must be correct. Does that answer the question? I think that's the case here.
So here there's a change in perspective where they're saying that there is a limit of there's an outer boundary for the galaxy, and we know where it is for the right plot, right? Which was not there in the previous plot.
Yeah.
I think the previous one they said that okay, it has to go as 1 over r to the 3 by 2.
Yeah, but this is not. Yeah, exactly. Yeah, exactly. So here, and that's a very good comment, because the very idea of that the galaxy had a bound disappeared here. And that's something that was very important, that you see mass growing and growing and growing. So where the actual bound of the galaxy was a thing that became very contested with these data. And that's also why it was quite controversial in the beginning, that they introduced a bunch of invisible mass that should exist, and also that there was no sense anymore of whether there was a physical bound to a galaxy. One of the questions that they started to discuss because of this. So what's interesting of this, and that relates again to the thing about what models of the universe exist, is that of course they also put it in that context. Oh, this is Jerry the Striker saying something about that they put together these different arguments, and there was no new physics involved in these cases, or new data. They put together these different arguments. That's the way that he put it in one of the interviews I did with him. And one of the other things that came in here is the sense of missing mass. So here's a very interesting quote from one of these papers. If we increase the estimated mass of each galaxy by a factor well in excess of 10, we increase the ratio omega by the same amount and conclude that observations may be consistent with a universe which is just closed, omega equal 1. A conclusion believed strongly by some for essentially non-experimental reasons. So for them, what was interesting here is that thinking about all these mass measurements or all these dynamical measures of mass, putting them together also gave a sense of the mass of the universe. And that's also the title of their paper. the mass, the number and mass of galaxies and the mass of the universe, I think is the name of the paper. So for them, it was interesting to make this cosmological claim to say that that if we increase an omega of 0.01 by 10, you only still get an omega of 0.1. But for them, it was enough to say that if that is the case, maybe there's more massing in even more mass that we're not seeing. So maybe we do live in a universe which is just closed. So this is a thing that they related to because that's what people did at the time. They related to cosmological models and what model in the universe that we existed. So what these papers did, I argue, is translate these open issues, these things that these flat rotation curves and the Zwicky problem in clusters of galaxies into evidence for dark matter. And very visibly so in that diagram that I showed you, they put all these things together as if they were data of the mass of galaxies and showed that if you do that, then these are actually the same problem. The problem that exists in the rotation of galaxies is the same problem as that exists in how clusters move apart. Before these papers, these issues were always treated independently of each other. And they showed, wait, what we can show here is that actually galaxies are much more massive than we see before. There should exist a halo or corona. So the Princeton group used the word halo, and the Asta group used the word corona for this new type of mass that should exist there. So now to close off, what I find myself to be interested in, often I get the questions, Jaco, who discovered dark matter? You know, who should win the Nobel Prize for dark matter? That's the thing that physicists often ask me. And this is an interesting question, but what I do want to show with this is that if you look at this and you want to pinpoint somebody, it's very, very hard. And even looking at this notion of discovery, looking at this notion of evidence, we need to try a little bit carefully to apply them without thinking about how a certain thing becomes considered evidence or how something becomes considered a discovery. And that is to get away from the sense of a discovery as being just discovering something and just pull away a sheet and then ta-da, there it is. Here we have found how I think there are good reasons to argue that some things do work, discoveries do work like that, but in this case, it definitely is not the case. So then my question is that, or my conclusion of this is that we should understand observations as not something that speaks for themselves. But for me as a historian, I would like to understand how observations started to become interpreted, and observations became something to speak for dark matter, because now if you show a flat rotation curve, then people would say, that is evidence for dark matter, but it wasn't just that in our understanding, or if we want to understand how the history of dark matter developed. So with that, I often then end up with that it might help to sometimes trace back where you were if you want to understand where your keys, where you lost your keys. And then that's how I sometimes want to justify doing a little bit more history in thinking about conundrums in science at the moment. So thanks for listening.
Maybe let's take about 5 minutes for questions. And if anybody on Zoom has any questions, feel free to raise your hands and I'll call on you.
Also, maybe turn on the camera.
Yeah, I was thinking,
yeah.
I didn't want to interrupt you.
Hello.
Yeah, so I had a question. So if you look at the very early universe, so what's the earliest trace available for the dark matter? Like just after the heating process, or the,
Sorry, what's the question?
like if you look at the early universe,
Mm-hmm.
so what are the earliest trace available for the dark matter?
There's what levels?
Like
Trace, you mean observational evidence?
observation traces, like
And that's something that they didn't discuss at that time yet. So that's for the understanding dark matter as part of the history of the universe was only a thing that people started to do much later in the late 1970s to early 1980s, and that was when the notion of particle cosmology started to evolve too. So the very idea of having an early universe and doing cosmology means to understand the early universe in terms of its particles, the particle soup, is something that came much later, and that was a decade later in the early 1980s. And what is interesting is that the understanding of dark matter as a particle that was part of that had to freeze out at one point to make sense of the structure of the universe is part of why particle cosmology became a thing in the first place. So dark matter, the rise of dark matter as a particle and the rise of particle cosmology or particle astrophysics, whatever you want to call it, came in tandem. But that's a decade later, and that's the chapter that I am currently writing to add to my thesis into the book. So how that developed in tandem. But that was only in the early 1980s.
So what's the current status like, or how what's people looking? So there was a model the pyramidal black holes can be candidate for the remnant. The pyramidal black hole remnant can be.
It can't account for all of dark matter. It can account for only a very small portion.
Yeah, now it can, but at that time. So, are you asking about the discussion of what was the dark matter?
Yeah, historically, or are you asking about the status?
Current status so if you're considering some weakly interacting dark matter particles.
Yeah. So I just want to interrupt. You're asking a non-historical question.
Yes,
is that true? Okay.
Yes,
so I'm not sure. Yeah. I'm not sure if I can answer. I give a good answer to you about that. But maybe that's something we can discuss after the talk. I'm interested in discussing more about that.
Thanks.
There's a question from Sam Fletcher in the Zoom. Sam, I think we can hear you.
Great. So you concluded that evidence doesn't speak for itself. That seems quite plausible. I was wondering, do you have in mind?
Now we do. Yes.
Should I start again?
Yes.
Okay. So in your conclusion, you suggested that the history here suggests that evidence doesn't speak for itself, and I think that there's a lot of independent evidence for that thesis, so it seems quite plausible to me. But I wonder, has anyone suggested otherwise? Is this something that people are confused about? Is that part of your motivation for advancing this thesis? Or if you have a different motivation, I would be interested in hearing about it.
Yeah. Thanks for the question. I'm not sure if it's a thesis other than a general remark. So this is, I think, I wouldn't develop this as a philosophical thesis, but I do. It's more of a remark to think about how we reflect around the history of the development of the field or a problem, and that we do not take for granted what observations are. So how observations are interpreted and as they are now. So yeah, I think the more interesting part of this how if we understand observations, they don't speak for themselves, then how should we understand evidence? What are the different ways that evidence comes into existence? And that's something that would be a more interesting philosophical consideration. And I think what happens here is this sense of a combination of different arguments that if you add them, when I interviewed Jim Peebles, he would say, if you ask me what was the best argument for the existence of dark matter, none of them. It was the combination of all of them that happened in this paper that made that this evidence start to exist. So there's something interesting about how something can become evidence in this story in particular.
But I mean, isn't the argument that you needed a theoretical framework that kind of puts these pieces of evidence on their own? Because if I remember correctly, Vera Rubin's 1974 paper where they present 74, 78, where they present the evidence does not cite Zwicky. So the connection was not made.
Exactly.
That these are all part of the
The
same.
same,
right.
so yeah, so they have the same explanation for a
Right, so
different
it
set
took
of-
the Yahil, whatever Stryker Peebles, that
Yeah.
paper before people made that connection across scales,
Yeah.
right? Yeah.
Does this help answer your question, Sam? Because I understand that. I think I take your point that are there other occasions that where this is not the case? I guess that's kind of what you're asking. So are there
No, that's not quite it. So because you framed your talk with this, I put it as a thesis, but you kind of wanted to demote it to something maybe less substantial. That's fine. But the fact that you framed it in this way made it seem that you think that it's quite important for interpreting the historical episode.
Yeah.
And I think
And I
that
think
the remark is quite plausible independently also of the historical episode.
Hmm.
And it made me wonder why you thought it was so worth emphasizing, because maybe I've just been in HPS for too long, but it's just kind of obvious to me. And so do you have contrasting statements in mind, situations where people have forgotten this and been led into confusion? What was your motivation for emphasizing this or highlighting this remark and
That's a
framing your
good
talk?
question. The motivation is so it's more of an argument for dark matter physicists who are often not aware of the history of these things, and they take for granted that flat rotation curves came into existence and were born as an argument for dark matter. And I think that is what happens a lot in historical reconstruction. And of course, it's not an HPS point that still is very substantial. But I think this is the thing, like a message that I often have for when I give the talk to physicists, is that although we now consider this line that people show, this flat rotation curve, as, look, people showed this the case, now it is dark matter, now dark matter should exist. That is not how this happens. So that is, I think, what I mean by observations should not be taken for granted, and that we should kind of historicize evidence as that's not something what I do here. You know, I don't historicize the notion of evidence, and I don't say evidence used to mean something else, but it is somewhere in there in the sense that evidence in this case, of course, is something particular in how it happened, and to understand the history of dark matter, we should unravel how certain things become evidence. So I don't think it's really a philosophical thesis, but yeah, if you have some more ideas or you have some, about that, but like you said, I don't think it's the most interesting HPS contribution.
But that's very helpful. Thank you.
Maybe we'll just do one more question.
Okay, it's not a question. I was kind of reflecting my own history, right? I started getting interested in astrophysics around 1980. These questions. I know that I read every one of the Rubin, Ford, Kent papers, absolutely convinced that, there has to be extra dark matter. It just was blindingly obvious. I did read the Oestreicher papers, more than one of them, papers.
Yeah.
I saw the Roberts paper on the flat rotation curve from radio. I don't remember Einastro for some reason. For me, the flat rotation curve was it. There was no need for anything else. I mean, what was there to be questioned there? I mean, it was just blindingly obvious. And I also was aware of the cluster business. So, the dark matter, I just absorbed it, even though it was so alien to all physics we know.
In what context were you? Was that astronomy or more physics context?
I was coming from physics,
okay,
but I was learning astrophysics, astronomy. So I was reading the astronomy literature really as a physicist. Yeah. And I was looking at it as evidence. So much so, I can say that within 2 years, when I started working with gravitational lensing, my go-to model for modeling a lens was what we now call the isothermal sphere, which is an object with a flat rotation curve, with mass spread out like 1 over r squared. And that seems so obvious. And it's not like there were others who were disagreeing with me. It was absolutely there in the community in 1980. Okay. So this has happened. 74, you say, was a big watershed. It completely missed me in the sense I was not even aware that 74 was such a big deal paper. it was Rubin and company that really convinced me.
Yeah, so these are two things I want to respond to that. First of all, it's a very interesting observation, and you're not the only one that I've spoken with, that in the 1980s, Vera Rubin had become a spokesperson for the existence of dark matter. Well, that wasn't the case when dark matter became a thing, so when dark matter became to matter. So her rotation curves, especially for the particle physicists who started to introduce these hypotheses, this sea of different candidates, were using flat rotation curves as evidence for dark matter. And she was still in the field giving talks to people showing these rotation curves. So that, I think, made her very important in the 1980s. But if you want to, my question is, how can I explain that? How can I explain that, given the fact that her work was, of course, very fundamental at the time, but why? So how did it grow? How did it grow that she became the central person to go to as the explanation for dark matter? Well, if you read the papers, it wasn't her early motivation for doing this. So I think that's an interesting observation.
I think there was a Santa Barbara workshop, right? There was a very famous Santa Barbara workshop in the 70s, I forget, 78 or whatever. Einasto, Batsumian, all of these people were there. The theorists were there. Rubin, I don't know if she was there or not, but that's when the rotation curves, that link was made with the CDM-ish papers were out already. And I think that's sort of what set, by the time Ramesh encountered it in the 80s.
No, I would say 79, 80, May even have been 78, but let us say 79.
There was a very famous review, which was very influential, which was written by Sandy Faber. That was in 1971, was a 50-page review that put all these things together and showed, well, we need to have dark matter should exist. But then at the same time, you have Cambridge cosmologist Simon White, who started working on cosmological models, and they started to introduce dark matter in these models. So they started showing that by the early 1980s, people knew that we need some extra mass to make sense of structure formation. And then the argument came that the Wimp miracle, that a particle could solve all these problems. And
that came later though. That came much later, right? By
1983, people, or 1982, 1983, people first used neutrinos to do this, but then the neutrinos didn't have the free streaming length that you too much, so it would.
When was Kolb and Turner? When was that book published?
1990, I think.
90, okay, much later.
But the cold CDM papers were already there.
Yeah, there was
83,
84 were the CDM papers.
I think we should wrap it up. But thank you so much for that.
Thank you.
Yeah, thanks.
I didn't mean to sort of butt in, but it's curious that.
Thank you very much.
Because I remember reading about this Santa Barbara